This week, we're getting into discriminant analysis. So the methods we focused on so far involve estimating differences in multivariate continuous response variables. So in MANOVA, we want to estimate multivariate continuous responses given group membership. What if we wanted to go the other way around and instead estimate group membership given some multivariate data? This is the idea behind discriminant analysis. One common example of this would be for the purpose of diagnosis. And so discriminant analysis is similar to other sort of binary outcome methods that we may have seen, such as logistic or probit regression. It's a little bit different. It uses a different technique. It has slightly more restrictive assumptions, but it can, when those assumptions are met, perform a bit better than the logistic models, but there really isn't a huge difference. It's sort of just another approach to a situation where we have binary response variable. So in this example, we're going to use the diagnostic example that I'm sure is still fresh in everyone's mind. So we're going to determine the probability of people having COVID or not having COVID given some variables about them. So in this case, we're going to look at their body temperature and blood oxygen readings. Let's start out by just assuming that we know that the mean vectors of temperature and oxygen for people with COVID and without COVID are 100 degree temperature and 96 oxygen level for people who are sick, and then 98.6 and 97.5 for people who are healthy. We're also going to assume that the groups have equal covariances, and that the covariance between oxygen and temperature is minus 0.04. So the higher your temperature is, the lower your oxygen level is likely to be. This is totally made up. This is another simulated data set. Don't take any of this literally. It's just a hypothetical example using something that I imagine we're all pretty familiar with right now. And so if we're interested in how these different distributions look, we can plot the densities. So I'm going to do a 2D density plot here. And so this shows the 5%, 50%, and 95% joint density ellipses for temperature and oxygen levels for the two groups. I didn't include the code. Don't worry too much about it. Feel free to look at the RMD files to see how I did it. But don't worry too much about what this code looks like. So there are your densities for the healthy and sick distributions. And so one thing to note is that they overlap quite a bit. In fact, these inner circles, which are the 50% densities, actually overlap. So that means there's going to be a lot of people who are sort of right, who are in the sort of like center of either one of these or both of these densities. So this really tells us that even in the best case scenario, there's going to be a lot of uncertainty as to whether someone might have COVID or not based on their temperature and oxygen levels alone. So the goal of discrimination is to use the information available to separate the two groups as much as possible, given what we know about the joint distributions. We call the variables that we use to assess this the discriminants. So in this case, the discriminants would be temperature and oxygen. So we want to find the linear combinations of our variables, our discriminants, that will maximize the difference between the two groups' mean vectors. So we can find these coefficients using this formula, where we subtract the mean vectors from one another and multiply them by the inverse covariance. And of course, most of the time we'll be estimating the means and the covariance matrix from real data and obtaining the coefficients using just the X bars and S, which is just the sample notation rather than the population notation. There are some different options for scaling the coefficients for the discriminant function. The book has a couple of normalizations that are different from what R uses. This is what R uses. That's actually not right. That's from an older version. The correct version will be in the class slides later today. It should be the square root of A times S times A, not the inverse of S. The goal of classification is related to discrimination, but it's slightly different. So in classification, the goal is to define some sort of rule that tells you which group a given observation is most likely to belong to. So when the discriminants represent the only information you have about group membership, your only goal and your only goal is to be as accurate as possible, classification is maximized by assessing which group mean each observation is closest to. So we can think of classification as if we're first identifying the midpoint between the two group mean vectors, and then drawing a line through that midpoint that's perpendicular to the line connecting the two mean vectors. So this splits the data in half and allows us to classify each observation based on which mean vector it's closest to. So the next slide shows the midpoint as a purple dot with several observations as black triangles, and we can classify the black triangles based on which side of the dotted line they're on. So you can see that purple dot's the midpoint between the two means of the two distributions, and then the dotted line here cuts right through that midpoint perpendicularly to the two distributions. And so whichever side of this line someone happens to fall on, we're going to classify them as belonging to the distribution on that side, with the mean on that side of the line. So to classify based on this discriminant function, we can use this formula, which evaluates to a scalar. And then any values greater than 0 get classified as sick, and any smaller than 0 get classified as healthy. I actually think I have that backwards here. It should be the other way around, but it doesn't really matter. It's just negative, just the difference between whether it's negative or positive. So I think this is the way it's written here. It would be the other way around, but the way we're going to evaluate it in R should be x2 minus x1. And maybe I'll fix that for the slides later. You just flip the x's around here, and then this is the correct interpretation. So far we've assumed that we knew the population means and covariances of temperature and oxygen for people with and without COVID. So now we're going to look at an example where we only have data to work with, and we're going to estimate it. So this is a data file that's up on Blackboard that was simulated based on the population means and covariances I told you about before. And so there are the three variables: it's temperature, oxygen, and then a binary variable, whether the participant had COVID or not. So there's what the data might look like. So we can use a two-dimensional kernel density plot to visualize the sort of empirical joint distributions. And there's the code for this is much simpler, so I put it up there. And so that's what that plot's going to look like. So you can sort of think of this as being like akin to like when we do a density plot for a normally distributed variable where we only have the data and it doesn't look kind of like perfectly smooth, or like when we have a histogram where it doesn't look perfectly smooth and we're trying to assess whether it's normal. So you see that these aren't like perfectly smooth circles. They're a little bit bumpy, but they are based on data that's drawn from a normal distribution, or two normal distributions. So the first thing we want to do is find the coefficients that maximize the total, that maximize the mean differences. So to do this, we first need the group mean vectors and the pooled covariance matrix. So we're going to get the means for each variable. Then we're going to count the sample sizes for each one. Then we're going to get the pooled covariance matrix. This is the same as we've seen before. And then we're going to get our coefficients by plugging into this formula. So these are our sort of raw coefficients. And then we can scale them with this formula. This is the correct formula here. I just forgot to change it on the other slide. And so these are our scaled coefficients. So to classify our data based on the discriminant function, we just compare these coefficients multiplied by the data points to this scalar here. And so then this will give us, this essentially centers everything at 0. That way, anything on either side of 0 will be classified as healthy or sick. And so that's how this would look. And so now let's go ahead and start using R to simplify our lives instead of doing everything by hand. So from here, we're going to use the LDA function from the mass package. It accepts formula syntax with the group on the left-hand side and the discriminants on the right-hand side. It's sort of like a reverse t-squared. And so note that the coefficients match our scaled coefficients. So we can use the predict function to get the predicted y hat values and classifications. This is going to give us both classifications and probabilities. We'll talk more about the probabilities later. So we can check our classifications against the ones that we got when we did everything by hand, and we see that they're the same. Just keep in mind that LDA converts the classification to a factor. And so you can check the levels of the factor either with levels, or here I'm just showing the STR to show you the structure where it's a factor. So we can check our classification success with a contingency table. And so here is the contingency table of our, where the rows represent the actual outcomes and the columns the predicted outcomes. So we can see that most of our classifications were good, but we did have some errors. So we classified 16 people who are actually sick as healthy and 19 people who are actually healthy as sick. So this next plot is again going to show this classification, and it's going to use color to separate how the participants were actually classified. And then it's going to use circles to represent cases where the classification was correct and X's to indicate where it was incorrect. And so there you see the X's are the incorrect classifications. And you see most of them are sort of here towards the center, which is where there's a lot of overlap between the distributions, but there's a few that are further out. So this blue X would be classified as healthy but sick. This red X would be classified as sick but healthy.